Ever look at a simple bag of flour and think about what it really takes to make it? I mean, really think about it? It's so much more than just grinding wheat. Today, we're going to pull back the curtain on the hidden world of a modern flour mill, where the very first tool isn't a wrench or a hammer, it's a calculator. This is the engineering of flour.
So let's just imagine for a second. You're given a job. Build a gigantic flour mill, one that can churn through hundreds of tons of wheat a day. Where do you even start? Do you buy the land first, figure out the building, order the giant machines?
Believe it or not, you start with none of those things. The real foundation of a modern mill, it's all math. Yeah, before anyone even thinks about a blueprint, engineers have to figure out a few absolutely crucial numbers that will define the entire factory.
So what are these, magic numbers? Well, they all come down to the two main pieces of the puzzle in any mill: the rollers that do the grinding and the sifters that do the sorting.
First up, we have something called roller length. Now, this isn't just how long one single roller is. No. It's an engineering term for the total amount of grinding surface you're going to need to process a certain amount of wheat in a 24-hour day. You can kind of think of it as the horsepower of the mill.
And what's really fascinating is that this number isn't one size fits all. It actually changes depending on the type of wheat you're using. You see, harder wheats need more muscle up front in what's called the break phase. That's the first crack of the kernel. Softer wheats, on the other hand, need more attention in the reduction phase, where everything gets refined. And the engineers have to know this from day one.
Okay, so once the wheat is ground up, you've got to sort it all out. And that brings us to our second key number: sifting area. This is literally the total surface area of all the sieves that are going to separate the good stuff, the fine flour, from the coarser bits.
And that whole sifting area is divided pretty carefully. It's almost always a 50-50 split. Half of it goes to the break system. Remember, that's for that initial cracking process. And the other half goes to the reduction system, which handles the finer grinding later on.
All right, let's zoom in on that break system for a minute, because this is where the real quality control is happening. Engineers have this concept called break release, which is just a way of measuring how good of a job each grinding stage is doing.
This table shows it perfectly. Look at the first break, B1. 100% of the wheat goes in. About 35% of it is small enough to pass through the sieve and moves on. The other 65%, they call that the overtail, goes to the next stage, B2. And you can see, with every single step, the amount of stuff going in gets smaller and smaller as the good flour gets filtered out.
By the time we get to that final break stage, B4, this whole process has been ridiculously efficient. I mean, look at that. Only 13% of what we started with is even left. Nearly 90% has already been sorted and sent off to other parts of the mill. That is some serious precision engineering.
And here is a super cool little detail right from the source document. At this very fine stage, the actual design of the grooves on the rollers, it's called the flute, starts to have a huge effect on what's left. It just goes to show you how every tiny detail really matters.
Okay, so that's the theory. But how does all this math actually turn into a factory blueprint? Well, you know what? Let's run the numbers ourselves.
Let's say our goal is to build a mill that can handle 120 tons. That's a whopping 120,000 kilograms of wheat every single day.
So here's how we do it. We start with our goal, 120,000 kilos. Now the formula needs a special number. In this case, it's 11.6 millimeters of roller length for every 100 kilograms of wheat. We just plug those numbers in, 120,000 times 11.6, and then divide that by 100. So, what do we get?
Boom! 13,920 millimeters. That's it. That is our magic number. That is the total roller length our factory absolutely needs to have. We're talking about almost 14 meters of total grinding surface.
But hang on a second. You can't just go out and buy a 14-meter-long roller. So what does this number actually mean when it comes to, building the factory?
It means this. The standard machines, the roller mills, they come in specific sizes. So, to get our 13,920 millimeters, we would need to buy and install exactly 7 of these specific machines. And just like that, the math has told us precisely how many of our most important machines we need. The factory is already starting to take shape.
And that's really the whole story right there. From just a couple of simple calculations, roller length and sifting area, an entire factory blueprint just emerges. The number of machines, the floor layout, how everything flows, it all starts with a formula.
So, the next time you're at the grocery store and you see a bag of flour, just remember the math that went into designing the very building it came from. Kind of makes you wonder, doesn't it? What other hidden calculations are quietly engineering the world all around us?